Okay, I think we're going to look at example 511, which is on page 120. So let's read that one first. So it says spacecraft at 2r sub e. What do you think r sub e means? Radius of the Earth, yeah. It says, what is the force of gravity acting on a 2,000 kilogram spacecraft? So it's pretty heavy. When it orbits the Earth, and it's 2 radii from the Earth's center, and it gives you the mass of the Earth and stuff. So how do you do that? I think first, at the Earth's surface, if you're on the Earth's surface, so here's the Earth, if you're actually on the Earth's surface, don't we already know about the force of gravity?
Negative.
The force of gravity is just whatever F equals ma, right? F equals ma, and on the Earth's surface, A is 9.8, exactly, g. Small g, right? We have a big G now. So on the Earth's surface, acceleration is that. So that's what the force would be if you're on the Earth's surface. This problem said, where are you?
2 times.
There's the radius of the Earth. So we're out here with another radius of the Earth, 2 radiuses of the Earth. Okay, so how would we change that? What do you guys think? There's not really 2 masses here, right? Like yesterday we learned the universal law for the force of gravity between any 2 masses. What was that? It's a good one to memorize. Capital G, which is another constant. Mass 1, mass 2 over squared. The most important part of that is this is like, it's what we're gonna see lots of relationships this year which have an inverse relationship where distance is squared on the bottom. Okay, that's going to happen a lot. It's called the inverse square law, in fact. It doesn't just work with gravity, it's also true for like some of the electric forces we'll deal with and stuff. So it's pretty common. It's called the inverse square law. Now we don't really have 2 masses here, so we just have the mass of the satellite, right? I guess maybe we have the mass of the Earth. But how could you do this? You know it's just mg for right there. So if you go farther away, what can you do with mg? How much is it going to be, less or more force? What do you guys think?
Less.
Farther away is going to be less force. How much less if you go twice as far away?
Half. Oh, no. 4 times less?
4 times less. Why 4 times less? Think about this.
Squared thing.
The relationship, whether you look at this stuff or not, the relationship with distance is if you go out twice as far, you have to square that on the bottom, right? So it's like you're plugging in. It's proportional to, remember there's this sign for proportional to 1 over r squared, and r was twice as much, so the force is decreased by 1/4. There's other ways to do that problem, but I really like reasoning through it that way because you guys haven't seen that reasoning very much before, have you? It's not a reasoning you're real comfortable with yet, but we'll keep reasoning like that in a problem here and there, okay? It's a little bit new. So it's a force mg. What's the m? Did they tell you how heavy it was? It's in kilograms, we're good, and g is 9.8, and you get your answer, whatever that is. What's it going to be in, though? I don't even care what it is, but it's going to be in, it's a force, it's in newtons. Excellent. Okay, moving on. Next problem. So there's a new way to reason through a problem without just plugging into the formula where you're thinking about the concept with the inverse square law. Okay? You might have been able to do that another way with the formula more, but I wanted to show you that way. So the book was good. Okay, let's look at 512. Read that one. I like this one. Could have put this on the vector quiz today too. Force on the moon. So it says find the force on the moon due to gravitation, basically, gravitational attraction of both the Earth and the Sun. And this is when they're in a very special relationship to each other. What's the relationship? Right angles. Would it be different if they were in another relationship to each other?
Yes.
Sure. So this is saying if they're at right angles and you have like the moon and you have like the Earth maybe over here and you have the Sun, I should probably draw them like to scale a little better at least, right? Earth. Is that to scale really? No, not even close. At least we have relative size then, right? So these are supposed to be right angles. Okay. So they said calculate the force of what?
The moon due to the gravitational attraction of everything.
So we just want the force on the moon from both things. How can we do that? Anybody have an idea? I guess you can
Just
cheat and read
find
theirs
the
if you want. If you want to skim it real quick and see if you can find the idea.
Find the resultant vector.
Find the resultant vector. Isn't that what you did with the gorilla a second ago? The answer on how to do that quiz problem was equilibrium means the things aren't moving. So you should add the one that was like this rope and this rope. The magnitude of those put together had to equal the gorilla pulling down for it to be in equilibrium.
Do you know what the answer to that last one was?
I
I'm not sure.
think it was 8.
That's not the very last one. The right one.
Show me the
We'll look at it Monday. Okay, let's not get too distracted. We've got a lot to do. So the idea is a resultant vector. Which way is the resultant vector going to be pointing, guys?
Kind of like,
Probably down.
well, it's probably angled towards the sun a little bit.
Force of gravity on the moon. So like, this one's pulling it that way. Sun's probably pulling it a little more that way. So it's probably going to be like more this way toward the sun or something, right? Something like that.
Yeah, but the distance to Earth is a lot closer.
That also might come into play, so we'll just have to see. So let's do it. So first we need this one, then we need this one, and then we'll result them to get the answer. Does that make sense? So first we need the first vector. Let's call it the force of the Earth on the moon. When you read this is the force of the Earth acting on the moon. It's how you subscript that doesn't really matter. Don't let it freak you out. You can call it whatever you want. You can write it in words if you like. I really like to do that.
Shouldn't it be towards the earth more? Because otherwise it would be smaller than the sun.
Yeah, well,
I don't know.
it's somewhere in there. We'll see what happens. Okay, force of the moon, the Earth on the moon. So how would I do that? I'd use the universal law of gravitation, which says G m moon m Earth, and then the radius, the distance between the Earth and the moon. Where do you think I can find those values? Where? Where? Front cover has values like that, or you could type into Google, right? Either one. If you're on like a test or something, then you should be able to consult a table. Like on the AP exam, they'll have a table of values like that. So let's see, is that in the table? Let's find it. I see an Earth-Sun distance and an Earth-Moon distance. Hey, Earth-Moon distance. It's in kilometers though, right? So for the radius down here, what should I put? It says 384 times 10 to the third kilometers, so I should put 3.84 times 10 to what for meters?
6.
That's one order much bigger, right?
7.
Does that make sense? Oh, yeah, because they said 384.
Yeah.
Right, is everybody okay with why that's to the 8th?
Yeah.
Because it was 384 times 10 to the third kilometers. So to go to meters, you make that 6. But to move the decimal point 2 more, you make that 8. Okay? So that's that, and we're supposed to do what with that? We're supposed to square that. Don't forget your square, you're going to die. It's always it's a hazard of living in physics land.
Is that radius?
Yeah.
Yeah, that's that. That's that distance. Anyway, so G, what is G? The value of G? Is there some constant?
Number.
It's on the problem. What does it say? 10 to the negative 11th newtons. Okay. Mass of the moon, it's on that page 2. What is it?
7.35 times 10 to the 27th.
10 to the 27th?
22nd.
Kilograms?
Yeah.
Okay, I'm just shoving this in. It's supposed to be like right here, but times mass of the Earth is. Good, it's bigger than the moon. That makes sense. We multiply all that together and we get that force, which let's just take the answer out of the book, shall we? Unless you guys feel like you need to do it. Make sure you can enter these in your calculator though. 1.99 times 10 to the 20th newtons. Okay.
So that would be just the x velocity, right?
Yeah.
Sort of, if we're thinking in terms
The force of the Earth to the
Yeah, it's like an x velocity. The way I have it pictured, I didn't have to picture it that way though, but yeah, you can call that like the x component of this vector that we're trying to find. Okay, so then you find the other force, which you're going to do the same way. Do we need to write it down? Yes?
If we could
Force of the sun on the moon, if you write it technically as that, but whatever. It's again the same relationship, so you've got G, so you're going to have that. You're going to have the mass of the moon, which we had from before was this one, right? And you're going to have the mass of the sun, which I don't know. What is that? It's got to be a lot bigger, times 10 to the 30th or something, I bet. Did I guess it right? 10 to the 30th?
30th. Yep.
I remembered some physics from all that time ago.
But you don't know the distance from the moon to sun.
It's right here.
It doesn't say it. Does it not say moon to
They
sun?
have it written down.
Oh, they have it written down?
I think they have it in our problem, but you'd have to look it up if it's not on your page.
Earth to sun and moon to sun.
What was it? 1.5 times 10 to the 8th kilometers. So 1.5 times 10 to the 11th meters squared. And then we get that answer, which we'll just take theirs. 4.34 times 10 to the 20th newtons. It's a little bit more than that one. So Jake's idea of distance, I think, did come in. It's not super a lot more than that one, is it? It's only like twice as big. So I think that's because of what? These two are much closer together, even though this one's mass is bigger. But this is way farther away, and it's still exerting more force. So then you use what to get the result? The net force, or the resulting force, you call that whatever you like, is equal to Pythagorean theorem, square root of
That squared plus that squared. And then you'll get a number.
Those are big numbers.
Well, doesn't it make sense that these are big numbers because these are like planets,
Big things.
planets acting on each other? Yeah, it's like the most significant force that you have for gravity, right? The only other thing that might be bigger is what?
Black hole.
Yeah, that's like a form of a star.
Galaxies.
If you have galaxies interacting, they exert a lot of gravity from the total mass of all the stuff in them. Yes, good.
Another galaxy is.
I don't know.
Yeah, those definitely ways.
Ways.
I don't
That
know.
would be
Maybe we'll be able to answer that by the end of
Every pebble of the galaxy.
the angle is just inverse tangent of y over x, right? What should we put for y? Which one of these is y?
The moon is
The sun.
Yeah, the sun one. So we could put that. So theta would be the inverse tangent of the sun one. This. Since they're the same order of magnitude, guys, do you even need to put that times 10 to the 20th in there? No, you don't, because it's just going to cancel, right? So you get that, and then I think they got like 60 some degrees. Yeah. So I think it was like, you guys were right. I think it was like 60. The theta you're doing that way is like right here. But whatever. Okay, so we'll move on.
I'm still right.
I am too.
We've got the idea. No big deal on that one, is there?
Wait, the tangent, the inverse tangent.
Yeah.
Or do you have to do the times 10 to the negative?
Right, that's what I was saying. You can put the times 10s in there if you want, but since they were the exact same on this one, won't they just divide out? Because it's all it's multiplied, right?
Be like 66.
Good question.
Well, yeah, but
Is it 24 versus the sun?
Make sure my video's still.
the other way back.
D66 that way.
Okay, let's see what else. I like this discussion. Let's just read this real quick.
Picture was correct.
I want to read the top of page 121. Can you guys just read that real quick? I think it's pretty interesting. I had a research assignment on this. Like, you have to go do research on it, but I don't think we have time. Anybody have a problem with that? Yeah, a little research on this. I don't think we have time in our lives.
No, I don't have time to do that.
I don't.
So I graded out of them.
Can I get some time for
This weekend's too busy.
Yeah.
Because I gave a lot of calc. So I'm going to ask a couple questions when you're done reading this. thought it was pretty interesting here. Can somebody tell me anything they thought was strange or something unexpected, or just what their impression is of what happened there?
We didn't know what the mass of the Earth was. We figured it out by knowing that and gravity.
Yeah, like how would you calculate the mass of something the size of the Earth? What are you gonna do? Put it on a giant scale?
That's what the cool kids do.
I mean, when you're trying to think about objects like that, like we need them, right? Didn't we just do that problem a second ago where we needed the mass of the sun? We needed the mass of the Earth? You always have to calculate those things directly or indirectly.
Indirectly.
You have to use like some kind of other argument, right? So the argument they used was, let's just think about the Earth's surface. Okay, here's the center of the Earth. Here's an object at the surface of mass m. And they said, just like we said a second ago, the force of gravity on the Earth's surface is just mg from Newton's second law, right? And g is 9.8 on the Earth's surface. That's been known for a long time, way long time, right? You can just measure how fast stuff falls,
I guess.
and you can find that 9.8 really easily. Like that's a lab we could do in this class. I mean, we'd have to be really careful, but
Is it exactly 9.8 or is that rounded?
it's rounded. We're gonna do something like that in a second. It's like 9.800 and then stuff. That's why it's rounded. Good questions. Anyway, so that comes from that. This comes from another source, right, which also describes gravity. This is applied between the center of the Earth and that mass. So it's got the mass of the Earth and that mass and this universal constant, which is another constant, right? And then the radius of the Earth. So I guess, so using some other technique before this happened, they had a way to guess, at least estimate the radius of the Earth. And the thing is, when you simplify, those cancel and you get g equals g, mass of the Earth, radius of the Earth squared. This had been known for a long time. This had been known for a long time. So these two, if you could figure out one of them, you could figure out the other one. And so how did that happen in history?
Big G.
They figured out big G first. We talked about that yesterday, right? This guy named Cavendish, a long time after Newton, like 100 years later, finally figured out big G, which allowed us to measure the mass of the Earth. And if you apply this on any other planet, you can find that planet's mass just as easily. Yeah.
How would they have calculated the radius of the Earth?
I don't know. I'm not sure. It's a good question. Someone's gonna have to look it up.
Simple.
I think it would have to do with maybe you go around like the Earth. You know how long it takes to get certain places. Couldn't you just measure the circumference? It's still an
It would
estimate.
take so long to get all the way around the Earth on a boat today.
But did people do that back in the 1600s? The Earth was first circumnavigated in the 1500s, 1600s, in the same era. So, pretty interesting. Yeah, I think that they probably did it that way. That's my guess. I'm not sure. It's
How
still
long ago did they find it?
which one? The radius? I don't know. I don't know. I'm not sure. Good question. We could look it up. I'll look maybe this weekend if I think of it. Okay, so there's how they did that. Let's just look real quick at 513 because I want to hit 514 for a while, and then we'll be done. So 513 says gravity on Everest. Yeah. 13. So estimate the effective value of G on Mount Everest. So now we have this relationship right here. So if we know those other things, we can find G. So how would we do that? We'd say G on Mount Everest. So let's say that this is now Mount Everest.
Radius plus the height of.
Okay, so the radius grows a little bit. It's a big mountain.
Yeah.
Okay.
Like it's deflating.
Like a peak
I'm gonna have to get Sheldon up here to do the drawing from now on.
It's like a little pimple.
Okay, so the mass of the Earth we know, right? What's the mass of the Earth? It's in that problem, I'm sure.
5.98 times.
I had these all memorized back in college. And the radius of the Earth we also know. We don't know where from, but somehow sailors or something. What is it?
6.38.
But we just agreed that on Mount Everest it's going to be a little bit bigger. So plus how much? 29,000 feet, but we need it in meters. Was it 8,000?
850.
So 8,000, so let's put 8.850 times 10 to the third. Is this third?
That's to the sixth.
Sixth, I think.
Yeah, that's gotta be way bigger, doesn't it?
Yeah, for meters, yeah.
It's making a
Oh,
little
right,
more
right,
sense
right.
to me now. Okay, so then you put those together and you've got the new value of G. Can you guys calculate? Use your calculator, don't trust them. Let's make sure we can get that in our calculator.
Is the 8.8 the height of Everest?
Yeah,
Okay.
Oh,
in meters.
so you have to add that.
Remember Everest? Remember we did those problems? Everest and all those peaks are 8,000ers, 8,000 meters.
Oh, yeah, meters.
You have to square the bottom.
And there's like,
Whoops. Yeah, I almost committed a fatal error. What, give me more decimal, please.
That's just what the book has.
I want you to use your calculator, make sure. So I remember in physics sometimes on tests, I would have problems like this. I totally knew how to do everything, and then I did something wrong on my calculator, and how many points did I get? 0 or half. Sometimes he'd be like, this is a couple professors I had, they'd be like, well, we'll give you half. I knew all the stuff, just entered it wrong. It's not fair. Life isn't fair.
No, you need to get Mr. Adair's number against 3.
What is it? 7?
9.771958.
Okay. Meters per second squared. Significant digits, we don't know it really that well, right? There's lots of estimating here. How well do you think we know it actually? Definitely not. No. I think that we are estimating the radius of the Earth too, so I'm not even sure if we can keep that last one. But it's pretty close to G, it's just a little bit less. Does it make sense that it's less than 9.8?
Yes,
Yeah.
you're farther away.
So you're farther away. Gravity has less effect. That makes sense. Good.
Earth is perfectly round.
Ah, so yeah, what other factors affect G? Do you guys think?
Wherever you are.
Where you are, like what?
Like elevation.
Elevation. So like G is going to be more where? Yeah, Death Valley.
bottom of the ocean.
Where would G be the most if you're going by that? What point on Earth?
Bottom of the Marianas.
The bottom of the Marianas Trench, G would be the most. Then.
Yes.
Very good. So that's why, besides the weight of the water, you'd also be smashed down there because you're so much
Even if there
more
wasn't
affected
water.
by gravity. Does that make sense? What else? What else would affect G? I don't think that's the only thing. What else do you think might have an effect?
North Pole, South Pole.
No, there's
Might
like
have a small effect.
Yeah.
currents.
What else besides your location?
Oh, yeah.
Uh,
The rotation.
Maybe.
What about
The sun.
I don't know. I don't know if rotation is going to affect it. I don't think so. It's a good idea, but what else affects gravity besides distance? What else affects gravity besides distance? Mass. So why am I saying
So like a fat person.
not the object itself? Think about the Earth. Is the Earth uniformly the same mass everywhere? Doesn't it have maybe pockets?
well, then there's America.
So if we're standing above a cave,
Yeah.
And we got
a big cave.
But I'm just saying the geology of the Earth might have an effect as well. Okay? Let's do one more. We'll be done.
They're really like.
What?
Is there a theory of the weight of the Earth? Like, I don't care, I wouldn't care if they.
The theory of like
Hologram, like,
geophysics is incredibly complicated. It's very, very complicated. Luckily, we don't need it for that many things, but
So, the mass that we're saying for the Earth is as close as we can get.
yeah.
And this is not including people.
Yeah, like the technique we've used, but that was described in history there, I'm sure has been improved upon. There's a better answer now, but
Well, the mass of the Earth is based on the effects of gravity.
And then you jump a class. it's
Yes.
like
Trying
stack
to
yourself.
actually weigh the Earth.
right, that's true.
So they add.
It's not perfect. Let's go on. We only have like 20 minutes almost, so let's look at 514, last one, probably most important one. Geosynchronous satellite. Okay. I kind of want to project this on the board. I guess I'll try to draw. Okay. A geosynchronous satellite is one that stays above the same point on the Earth, which is possible only if it is above a point on the equator, okay? Such satellites are used for TV and radio, blah, blah, blah. Determine A, the height above the Earth's surface. So if you wanted to keep orbiting that same position, how high does it have to be? I think there's a very specific height. So when they launch satellites, they got to hit that height perfectly and slow it down just right. And part B is how fast does it have to move? It's a very specific speed. And then part C, we'll make a comparison if we have time, we'll see. Okay? So part A, what did they do first? Let's try to read the book's example and learn how to do it quickly. So what did they do? They put F equals ma. That's just Newton's second law, sure. So then we apply it to our situation of a satellite. Right, so here's the Earth, here's the satellite. I don't know how far it is out there. We say F equals ma. Hey, we know another way to express the force of gravity. It's what? Gmm over r squared. So we say, what are the two masses? We've got what?
Satellite.
We've got the satellite and the Earth and the radius. That's what we're trying to find, isn't it? That's how high it is going to be. Does that make sense? Okay. So then what do they have on the other side? ma. M is what again? Satellite. Acceleration. Do we know anything more about acceleration? This isn't on the Earth's surface, so we can't put g. Little g. What could we do though? What kind of motion is this? What's this whole chapter about? Circular motion, and things that are moving it with circular motion, the acceleration can be expressed how? Excellent.
Do we know V squared then? Or V?
Good question. So how can we find that? That's a real key to this problem. That r is still going to be this r, right? Like this is the same r. Because this is the same r. You guys all play with that? Like this r is between those two, but it's also the radius of that movement in a circle. So Paul said the real problem here is now we don't know v. Don't we have another way to express v when we're moving in a circle? We talked about yesterday. Remember the thing I couldn't remember for a second? Where it came from? That distance equals rate times time becomes what? V equals over the period. So we can stick that right here. Oh, the mass of the satellite cancels, doesn't it? Okay, we just go chop, chop. This is looking ugly, but I don't think it's that bad. So we've got a g, that's just a number. Mass of the Earth is just a number, nice and friendly. I could even multiply this r up here, can't you? Like multiply this r over there, and that cancels one of those. Okay, that's looking better. Then we've got a 2 pi r over t squared. Does that make sense? I think that's okay. We know that r is just the same r we're searching for, so that this is constant. The only question is, do we know t? T is what?
Period.
Period of
Circular.
the period of that satellite circle. Which, what would that be if we want it to be geosynchronous? A day. Satellites move fast. If they're in the geosynchronous orbit, they're supposed to like come back to the same point every day. So this is a day. So how do we put a day?
In seconds?
24 hours.
Remember, 24 hours times 60 minutes in an hour times 60 seconds in a minute. What is that? Also a nice thing to remember. What is it? 8.6 times 10 to the...
86 seconds in a day.
Is it fourth or fifth?
It's
86,000, isn't it? I think it's fourth. Okay, so now all we've got to do is move stuff around and solve for r. These are just numbers. I'm not going to put the numbers in. You can if you want. Why? Because I don't want to write down big, giant scientific notation over and over again. I'm just going to remember these are numbers, and that r is my only variable, so I need to get r by itself. So I'm just going to move stuff around. What should I do? I don't know. It's up to you. I'm going to put this r over there. So how many r's are we going to have over there? Three of them, r cubed, right? And then on the other side, we're going to have a g, the mass of the Earth. This is going to multiply up on top 2, isn't it? That same red thing. So should I just put 8.6 times 10 to the 4th? It's in the squared, so it should be squared, shouldn't it? And what else? Divide by the 2 pi r.
Squared.
Divide by 2 pi
Square.
all squared, not just 2 pi squared, 2 pi the quantity squared, yeah? And then I've got it. So what's the last step? Get rid of cubed, cube root. We all know how to do that on our calculator, do we remember?
That thing to the 1/3
To the
power.
1/3.
To the 1/3, right? So you'd put all this in your calculator, use alpha y equals if you're smart, so you don't mess up. Use alpha y equals, put all that stuff in, and then put, instead of 8 that, you're gonna put to the 1/3 for cube root. Okay? You get your answer. Questions? It looks ugly, but I don't think it was too bad. It just looks ugly.
Now, since I try to do it by myself at home.
Okay, part B. Part B. Who are making good time? Very nice.
Hold on.
Part B, we're supposed to find the satellite's speed. Okay.
Very close.
Because you know the radius now.
Yeah, I think you can just plug it in wherever it's convenient. Where is that?
Would be
Because our
the time is 1 day.
we moved
Rate
the
times
R
time equals
over
distance. So R.
I guess it depends where you're at in your equations. You could just plug it in right up here, right? So maybe I should simplify this part right here and make it nicer. I'll try to do that over here so it's in the video. So we've got, go ahead.
Now you know R, so that's just do the simple rate times time equals distance.
We could use this one. Yeah, sure. We could use that one. So what do we do? 2 pi, what is the R they gave us after that calculation?
4.23 times 10 to the 7th. Tim?
Where are you getting this?
From the book. It's this answer.
Then it's just 8.6 or 7.4.
But I thought for R they got like 7.54 times 10 to the 20 seconds.
M3.
Meters cubed.
Yeah.
Right. So then that's just when you take the cube root. Yeah.
Yeah. That's weird. See, the book did it a freaky weird way. Silly, right? So anyway, it's this. That's the radius you come up with if you type that in your calculator. And then the period we said again was the same thing, right? So 86,000.
Times 7.4.
So 86,000. That's 86,000. Okay? So let's see what we get. Type that in your calculator. You guys do it because the book did this a totally different way. I think that that's totally a good way to do it. I'm glad Jessica saw it. Hope you did, Davey, too. Because that's going to be a big key on your problem, so we'll talk about that in a second. See if we get the same answer as them first, though. I hope so.
3090.
They got
37.
30 what?
3090.
Yep. I think there's just some rounding issues. Sweet. So how did they do it? I think that they went up back in here and simplified this and solved for V right here, right? So you can solve for V like that. What is the answer when you do it? Let's see. What did they do? They said one way to, if you're messing with this, you have, let's look at it. GR squared equals mass of the earth, excuse me, equals velocity squared over r. So if you solve for v, you get the square root of one of the r's cancel, gme. So that's one way to come up with a velocity of something that's moving in this kind of a circle. But then we have another way to do it. So do you think in some problems you might have to equate those two expressions and say this equals this? Yes, I think you'll have a couple problems like that. So realize that you've got two different options for circular orbits. You could calculate velocity this way or this way. And I think this problem will probably be the most helpful for a lot of your ones in the homework toward the end. Yeah, it was definitely in this one. It was easier, for sure. Good choice. Okay.
How many
So I
of
think
these
we're good.
equations are we gonna have to memorize?
For the physics, remember, if you take the AP test, they're gonna make you memorize like the most important ones. For my test, I don't know. I'll let you know. I'll give you some, and then I won't give you some. Like I won't give you the kinematic equations. I probably won't give you universal gravity, but like this,
Okay.
yeah. If you need that, I'll be giving you that. This, I think, is just distance equals rate times time. You should be able to derive that yourself again real quick. Just think, hey, circle, there's the distance, the rate, and the time. That should be something we can do. You know what I mean? But I'm not going to overload you. We'll feel it out as we go along, so. Okay? All right. We have enough time to watch a thing on Kepler's laws. So.